video for chapter 14. This is a video just doing a bunch of past HSC questions. If you haven't watched the first video where I go through the content and the topic, I definitely would suggest you check that one out first. And as you are watching this video, what I would suggest you do is every time I go to a new question, pause it, have a go at the question yourself. Then once you've had a go at it, watch my solution, because that way if you get it right, sick, you got it right, and if you didn't, well then you can see how you got it wrong, and hopefully you'll learn from that as well. Anyway, we'll just get straight into this. So looking at this first question, the benchmark of an annual greenhouse gas emissions for the residential sector is that much per carbon dioxide per person per year. And this new building planned for 6 people is designed to achieve a 25% reduction. So we've got 6 people, 25% reduction. What is the maximum amount of carbon dioxide per year to the nearest kilogram, so enjoy reading that is this building is designed to emit when fully occupied? So I mean, that means it is going to be 6 people. So there's quite a bit to unpack here, but basically what we're seeing in this question is this new building that's being made is going to be doing 25% better than that 3,229 kilograms. So let's first of all find that. So we've got 25 over 100 times 3,292, which is 823. So therefore, if we're going to find, that's how much better they're going to be doing. So we want to decrease that. So we're going to do 3,292 minus 823, which equals 2,469 kilograms per person. Alright, so what we're saying here is, each person that lives in this house, they'll be emitting about 2,469 kilograms of carbon dioxide per year. Alright, and so essentially, that's for one person. We have 6 people, so we're just going to do 6 times 2,469, which equals 14,814. So the answer is D. So that's the first question. There's quite a lot in there, but basically what we're saying is we had, this much, but in this house they're doing 25% better. So find what that 25% better is, which is 2,469, and there was 6 people, so we just have to times by 6. Going into this next question, this is, the very first question, the free response part of last year's paper, so it should be pretty basic, and it is. Basically, you're saying electricity costs that much per kilowatt hour. How much does 20 kilowatt hours cost? So it's literally just 20 times 0.27, which equals $5.40. That's it. So going on to the next question, it's simple as that. And it's the first question, the free response. It should be quite basic. Going into this one, question 9. An old washing machine uses 130 litres of water per load, and a newer washing machine only uses 50 litres. So basically what we want to do is find how much water is saved each year. We're using 2 loads of washing each week. Okay, so that's an important part of it. Okay, otherwise it'll just be 80 litres. We need to know how many loads are being done. So what I'm going to do, there's 2 ways of doing this. I could find the difference, which is 80 litres, and then find how much water would use in that 80 litres. What I'm going to do instead is find how much water is used with 130 litres. So it'll be 130. And then we're doing 2 loads every week. So we're going to do times by 2 and times by 52, because there's 52 weeks in a year, which gives you 13,520 litres. Alright, so that's how much water is used in a year for that older machine. And for the newer machine, we'll do 50 times 2 times 52, which equals 5,200 litres. And so now what we want to do is, well, how much water is saved? So we're just going to subtract these 2 numbers. So we'll do 13,500 minus 5,200, which equals 8,320 litres, which is your answer. That's how much water was saved. Alright. Going to this question now. I'll make the screen for this one. So the cost of buying a new heater is $990. it uses energy according to the following labels. So you might have seen these labels if you walked around like JB Hi-Fi or Good Guys or Harvey Norman or whatever. And it kind of has like an energy saving star index and all that kind of stuff. And we see in here that the energy consumption is 505 kilowatt hours per year. Right? And energy is charged at the rate at 35 cents per kilowatt hour. So essentially what we want to do is how much will it cost in total to run it for 5 years. So we need to read that part carefully. Not only the 5 years, but also in total, cost in total. So we'll get to that bit in a second. But let's first of all calculate for 5 years. Well, we saw that it's 505 kilowatt hours. So we're going to times that by 35 cents. And that's for 1 year. So we're just going to times that by 5 for 5 years, which equals $883.75. But that is not the answer just yet. That will get you 1 out of 2. Because the thing is, like I said, how much does it cost in total? That includes actually buying the heater in the first place. And we're told in the question that it costs $990. So therefore, we're going to do 990 plus $883.75, which equals $1,873.75. That's where that second mark comes from. So you've got to read the question carefully there. It says how much did it cost in total. That means actually buying the thing in the first place. Going to the next question. This is starting to get a bit harder because this is question 30, like the first question of question 30, but still question 30. So we're told that the area of the roof is 30 meters squared. Any rain that falls on the roof flows directly onto the garden. So this is what I was talking about in my video. Like the way that roofs are created in Australia nowadays is like it's quite efficient. What it does is it catches the water that falls on the roof, goes into the gutters, and then it just recycles that water. So we're saying that all the water that's going into the roof is being caught by the roof, goes straight into the garden. So we want to calculate how many litres of water flow into the garden when 20 millimeters of rain falls on the roof. A way that you can kind of visualize this, I'll just do this really quickly before we go into the actual answer, is like say here's our roof, okay? This is, there's our roof. We know what the area is, it's 30 meters squared, right? And what we're now doing is say, so it started raining, and then, so there's like a layer of water, I guess you could kind of think on top of it. Alright? And the height of that layer of water, as it says in the question, that's a shocking diagram, but whatever, is 20 millimeters. Alright? And essentially what we're trying to do is we'll find how much water, like what's the volume of that very thin rectangular prism. Okay? So what we need to do first of all, we can't just do 30 times 20 because as we know, volume equals the base area, which is, we already know to be 30, we need to times it by the height, but they need to be in the same unit. Okay, so we have 30 meters squared, we now need to change that 20 millimeters to be in meters. So 20 millimeters, what we do is we can divide it by 10 to get 10 centimeters, and then it's not 10, 2 centimeters, and then now if we have 2 centimeters, we're going to divide it by, we're going to divide it by 100, and that's going to be 0.02 meters. And so now that we've got that, we now need to find the volume, because now they're both in meters. So volume equals 30 times 0.02, which equals 0.6 meters cubed. So that's, halfway there. That would be the 1 mark, because again, this is out of 2. So 1 mark is just find the volume, but we want to find how many litres, okay? So we need to change these litres, this meters cubed into litres. And like I said in my video previously, or just if you just notice on the formula sheet, we're told that 1 meter cubed equals 1,000 litres. So essentially, we're just going to get this 0.6. I'm going to times it by 1,000, which equals 600 litres. And that's your answer. Okay, so what we needed to do is find how much water in meters cubed fell onto that roof, which we found it to be 0.6 meters cubed, and then we just converted that into litres. So So, going into this next question, and I'll just zoom in a bit. And in this question, as you see, I've just added a few markings here, and I said this in the video, it's really important that you have your ruler in this test, because like it gives you this question, right? And you need to find the scale itself. It doesn't tell you what the scale is. It does tell you a little bit. It says that this dotted line, so the width of the shed, like this dotted line is approximately 12 meters. Okay, so that dotted line that I've got there, if you got out, like, if you printed out this piece of paper and got out a ruler, it would be about 4 centimeters. So that's what I've done there already. And then the width of it is 6 centimeters, which we'll use in a second. So by measurement and calculation, show that the area of the roof is approximately 216 meters squared. Alright, well, what we can do is let's find the scale on this map. So we're told that this 4 centimeters actually means 12 meters in real life, right? So once we've got that, again, like I said in the video, is we want to change that to be 1 centimeter, alright? Scales aren't very useful unless they're in like a singular unit. So here we divided that by 4, so that means we also need to divide that by 4. So it gives me 3 meters. And so now we have 1 centimeter equals 3 meters, therefore the width, which I've measured there, is 6 centimeters, so we do therefore 6 times 3, which equals 18 meters. So then the length, the width, I don't know whatever you want to call it, is 18 meters. So we know that if I were to write this on this now, I know that this is 12 meters, and I know that this is 18 meters. So now to find the rectangular area, we're just going to do length times height. So therefore the area equals 12 times 18, which you can probably guess is 216 meters squared. Of course, this is approximations because, you know, this photo isn't perfect and our scale isn't perfect, but, you know, that's all we can really do. Alright, now going into this next question. So this is very similar to that roof question we just did a second ago, except it's also a lot more difficult. So we'll just have a go at it for a second. Before we do anything, well, let's look at this question. So we're saying that all the rain that falls onto the roof is then put into a cylindrical tank with a diameter of 3.6 meters. During a storm, 5 millimeters of rain falls onto the roof. Therefore, that means 5 millimeters then goes into that tank, but it's not going to be exactly 5 millimeters in the tank. So calculate the increase in the depth of water in the tank due to the rain that falls into the roof during the storm. So I'm just going to do another really good drawing over here for a second. So here's our cylindrical tank. Okay? We know that the diameter is 3.6, right? We're told that in the question. And let's just pretend like we had, you know, some amount of water in here already, okay? And then afterwards, we're told that, you know, after some more water came in, so let's say that blue line is where it is now, okay? So from that, essentially what we're trying to do is we're finding the increase in depth. So rather than trying to find the whole height, we just want to find like the height in here, okay, from where it started to where it is. To do that, we're going to need to find the volume of water that was caught in that storm, which makes it very similar to the question that we just did. So we just found, like, remember, volume equals the area times the height, okay? And, well, we know that the area was 216 from the previous question, and we got the 5 millimeters of rain, and again, if we divide it by 10 to make it into centimeters, and divide it by 100 to make it into meters, because again, they need to be in the same unit, so this becomes 0.005 meters. So we're going to times by 0.005 meters, which equals 1.08 meters cubed. So what we're saying here is the volume of this new water that's gone into this tank is 1.08. So we're kind of going to use the volume formula in reverse. Remember, the volume formula is usually the volume equals that base area, but because it's a circle, it's going to be pi times the radius squared times the height. This time we know what the volume is, we know what the radius is, we're trying to find the height, so we're going to actually do it in reverse. So if we were to set up this equation for us, we've got 1.08 equals pi times the radius squared. Remember, the radius is not 3.6, it is 1.8 because it's half of the diameter. And times the bar height, oh sorry, I should square that, times the bar height, which is what we're trying to find. We're trying to find what that difference is. And then so now we'll just divide it across. So say that h equals 1.08 over pi times 1.8 squared, which equals approximately 0.106 meters, just 3 decimal places. And that's the answer. Now, that is quite a tricky question. And, you know, looking back on the stats for that year, the 2015, out of 3, the average was 0.42 out of 3. So what that means is a lot of people do know how to do that question. I would say quite a few people probably got up to there and then just didn't know what to do. And yeah, that's, you know, hazard to say that's probably the hardest question in the whole paper. It's only in question 29C. Yeah, anyway. So, going on to this next question. The next two are quite a bit easier. Like, that's definitely the hardest question in this video. So looking at this one now, this one's actually quite difficult as well, but I wouldn't say as difficult. Anyway, so here we have this situation where the energy consumption of a computer in standby mode is 21 watts. The cost of electricity is 31 cents per kilowatt hour. Okay, so there's going to be quite a few changes that we're going to need to do here, because right now we have watts, and eventually we want to get to kilowatt hours. So we're told that in this computer room there are 20 computers. Alright, so how much will the school save by just switching them off for 11 weeks during the school holidays? Okay? So the idea is right now they just keep them on throughout the holidays. If they were to turn it off, how much money would they save? Alright, so first of all, let's just find how many watts are being used. Alright, not kilowatt hours, let's just find the watts. Alright? So the watts here, we're told that, you know, the energy consumption is 21 watts per computer, but we're told that there's 20 computers, so we're going to times this by 20. Which equals 420. Alright, so that means there's 420 watts being consumed, which if we want kilowatt hours, we want to change that into kilowatts. So let's go ahead and find this to be 0.42 kilowatts. Alright, so that's a decent start, but we want to eventually find kilowatt hours. And remember in that video, the way that you're going to find that is you get the kilowatts, and you times it by the amount of hours. So what we need to do now is find out how many hours are these computers are sitting here. So the way we're going to do that is, well, we're told that it's over 7 weeks. Okay? So, 11 weeks. So we have 11 weeks, times it by 7 because there's 7 days in a week, so we have 77 days. And then we want the amount of hours. So we're going to now times this by 24 because there's 24 hours in a day, leaving us with 1,848 hours. So what we're saying here is, over these 11 weeks, if you add up all the time spent, like with all those 20 computers, a total amount of 1,848 hours have been used. And so now we want to find the kilowatt hours by, like what I said, we're going to find the amount of kilowatts, which was 0.42. We're going to times it by the amount of hours, which is 1,848, which equals 776.16 kilowatt hours. And now that we've got the amount of kilowatt hours, which is what we want, because the question now says was 31 cents per kilowatt hour. So therefore, we'll just at the end do 0.31, we're going to times that by 776.16, which equals $240.61. And that's how we find that one. So quite a bit here. I mean, the main trick to this question is realizing that it's 21 watts for the computer. So if we have 20 computers, that's 420 watts. We want to change that to kilowatts, so we divided it by 1,000 because, as I said in the previous video, kilo just always means 1,000. And then we want to find the kilowatt hours, so we calculate how many hours were there, multiply the two together, and then just found how much that costed, because once we have kilowatt hours, you're basically done. And then lastly, this question here is involving two usages of Simpson's rule. So it's a bit of a long question for what is really only 1 mark. So it's a bit annoying in that regard, but we'll just do it anyway. But the main thing you need to do is realize that we want to do, like it says we want to use Simpson's rule twice, right? So we're going to do the first half, I'm going to do that one in red, and then the second half is when we're doing it in blue, right? Now, that whole distance is 8 kilometers, so that means this, from that red distance is going to be 4 kilometers, but remember that's not going to be our h. What we actually want in here is 2 kilometers. And that's what our h is going to be in each of these things. So remember the Simpson's rule for volume is approximately equal to h over 3, and then the first area, so AF, plus 4 times the middle area, which is AM, and then the last area, which we'll call AL, and then you just find that it's approximately equal to. So we're going to have to do this twice. One for the first half, one for the second half. So I'm just going to call this V1, and I'll call this V2, and at the end we're going to add it up. So the first half is V1, second half is V2. So let's find V1, and that's approximately equal to 2 over 3, and then 6.2, so that's that first area, you see in the far left, plus 4 lots of that next one, which is 8.1. And then we're going to do 7.3 at the end, and that equals approximately, or that does equal 30.6. And then if we do the same for the other half, so V2 is approximately equal to 2 over 3 once again. And now we're starting at the middle, so we're starting here. So we have 7.3 plus 4 lots of 7.1, so that's the next one. And then lastly, 6.0, and that equals 27.8. And therefore, if we're going to add them together, so V1 plus V2, that equals 58.4, which is closest to B. Anyway, so I've chosen those questions. There are a few more in Project Maths, but I've chosen these questions because it kind of gives you a good variety of all the kinds of questions that they ask. The main things you really want to know is, volume of like rain catchment, so those are the ones where water falls on the roof and then goes into the container and all that. And the other thing you want to know is the power usage, so like the kilowatt hours, being able to change watts and kilowatts into kilowatt hours and doing all that kind of stuff. Again, if you have any questions regarding these, make sure you ask, and hopefully this video is useful.